Welcome to the Chapter 2 Part 1 Notes video. Sorry I can't be there today, but this video will talk you through the notes. A lot of this should be review, starting with Chapter 2. As usual, we have a Formulas and Big Pictures page. On the back of that page is where we're going to start with the 2.1 notes. I know a lot of you use the Formulas and Big Picture page for the chart. We'll go over your exploration next class when I'm returned to school. So we're going to start in with vocabulary. You know that I like to help you construct the vocabulary together, but a lot of this will be review. So I'll just kind of dive in with the definitions. And then if you have any questions, make sure to jot them down so you can ask them when I return, and we can make sure to clarify any questions that you have. Our first vocabulary word is degree. We've talked about the degree of a polynomial before. The degree is going to be the largest exponent on a variable. So the largest exponent specifically on a variable. When we have a number raised to a power, that does not count as a degree. So our example here will be something like 5x squared minus 7x cubed plus 12. We have two variables here. The first one has an exponent of 2. The second one has an exponent of 3. That means our degree is 3. Our next vocabulary word is coefficient. We've talked about coefficients before as well. Coefficients are the number multiplied to a variable. A number multiplied to a variable. If we look at our example above, we have two coefficients. We have 5 and -7 as our coefficients. 12, remember, is actually called a constant, but we treat constants as coefficients as well. So we will call 12 one of our coefficients. When we talk about coefficients, a lot of times we want to refer to a leading coefficient. And we've talked about leading coefficients as well. So again, a lot of this is review. Our leading coefficient is the coefficient of the term with the highest degree. So it's not always going to be our first coefficient. Here, our leading coefficient is -7. So the coefficient, and I'm going to abbreviate that, of the term with the highest degree. So for ours, it's -7. Okay. Now, when we talk about polynomials, polynomials can be a single term or it could be multiple terms. So when we're talking about polynomials, we're talking about the sum of terms that have degrees that are only whole numbers. And we talked about this a little bit when we were doing the exploration. So a polynomial is the sum of terms with whole number degrees. Now, there's a very complicated way of writing a formal definition of a polynomial. A polynomial is a function where we have n terms. We've seen this notation before. A sub n is just going to be an n number. The subscript just differentiates it from our other coefficients. So a is our coefficient. Then we have x to the power of n. Then we have our n-1th coefficient for x to the power of n-1. Notice we have our subscript matching our exponent all the way down to our first degree term with our a sub 1 and our 0 degree term with our constant. Okay, now this is fancy notation. I won't expect you to recreate this. However, if you do see it, you should think polynomial. A couple special polynomials that we're going to focus on today are our linear polynomials. A linear polynomial is degree 1. The degree is 1, so that's something like y equals 7x plus 13. Okay, a degree 1 polynomial. And then quadratic is degree 2. Something like y equals 9x squared minus 4. Okay, now I'm writing so far, all the polynomials I've given are multiple term polynomials, but a monomial, a one-term polynomial, is also could be linear or quadratic. So y equals just x squared. That is also quadratic. Okay, we've seen a lot of examples of linear and quadratic equations. So I'm not going to create an additional list, but feel free to kind of nudge one of the people sitting next to you and confirm if you understand or if you have questions on linear quadratic. Let's look at an example here where we're going to look at whether or not something is a polynomial, identifying the degree and the leading coefficient. So some of the vocabulary words that we just defined. The first thing I'm going to check for part A, we're looking at a polynomial means that the exponents on the variables are whole numbers. We have 3, invisible 1, no variable. So this is a polynomial. For the degree, I look for the biggest exponent. So 3 or 1, which one's bigger is 3. And the leading coefficient, if 3 was my degree, the coefficient of that term is 4. On our next one, we want to know, is this a polynomial? Our exponent is -4. Well, -4 is not a whole number. -4 is negative, right? So as a reminder, I might put over here whole numbers start at 0, 1, 2, 3, and so on. Does not include any negative numbers. So actually, part B is not a polynomial. And if it's not a polynomial, we're not going to worry about the degree or the leading coefficient. In part C, I'm looking at my exponents. Now that looks like an x to the 4th and an x squared, but because it's in a radical, we could write this whole thing as to the 1/2 power, and 1/2 affecting a variable means that this is not a polynomial. And then part D, we have our exponents 1 and 4. Those are both whole numbers. So this is a polynomial. The bigger degree is 4. And so our leading coefficient, and be careful, is -2. When we're classifying our polynomials, we do have the 0 function. We have to be careful with whenever we have y equals 0, because the degree is actually undefined. And if we think about that, the degree for a horizontal line that is on the x-axis is going to have infinitely many points that intersect the x-axis, infinitely many zeros. And that's what causes the degree to be undefined. So we just have to be careful about that 0 function. It is still linear. It creates a line, just like our constant function, which we can classify as a line. So really all 3 of these are lines. And then we have a quadratic function, and we know that a quadratic function is a parabola, right, from our 12 basic functions. In example 2, we're graphing a linear function. Now we have practice from this from our art project as well as from our previous notes. So really what we're focusing on here that's new is the notation, right? F of x is the same as y. F of x is y. So that makes this is an x value. This is a y value, x value, y value. That means I have 2 ordered pairs here. The first ordered pair is -1, 2. The next ordered pair is 3, -2. I'm going to have you calculate this, and then I will show you the answer. You're going to have the opportunity to type in the equation of the line that you get into Edpuzzle, and then I will show you the answer so you can proofread your work. Okay, so after finding the slope and using the point slope formula, you should get the equation y equals -x plus 1. To graph this, I put the y-intercept at 0, 1 with a slope of -1/1. And so we can fill in all these points to make as straight a line as possible through all these points. And if you have a ruler, you can always grab a ruler from underneath the flag. I always have rulers there. If you're doing this at home, you can use any straight edge, or if you draw in enough points, you can just kind of connect the dots and make it as straight as possible. Okay. Moving on to our next example. In example 3 on the next page, we're looking at average rate of change. Now, the average rate of change is the slope between 2 points. What I want you to think about is, how do you think this is different from slope, right? The average rate of change calculates slope between 2 points. And my hint to you is think of higher degree polynomials. Higher degree meaning maybe something quadratic or cubic. Try picking a few different points to see if you can find the average rate of change. Hopefully some of the things you might have thought of or discussed is that for a line, slope is constant. So if I draw a line here, no matter which 2 points I choose, the slope will always be the same. But the average rate of change can fluctuate or change. So if I pick 2 points on the parabola, I might get a certain slope, whereas if I pick 2 different points, I will get a different slope. And the same thing for our cubic function. Depending on the 2 points I choose, it could be the same slope, but it could also be a different slope between those 2 points. So what I want to do now is calculate average rate of change, see what that looks like. And the key is going to be looking at the 2 points that we're calculating the average rate of change between. So the first thing I want to do is calculate these 2 points, f of -1 and f of 3. And we do that by substituting in for x. 3 times -1 plus 1. -3 plus 1 is -2. That gives me the ordered pair -1, -2. Then 3 times 3 plus 1. 9 plus 1 is 10 for the ordered pair 3, 10. You're going to go ahead and calculate the slope between these 2 points, similar to what we did in example 2, and then do the same for parts B, C, and D. I will pause the video, have you input your answers, and then go over the answers together. As you might have noticed in part A, this is actually a linear function. So no matter what 2 points we choose, we should get an average rate of change of 3. For the quadratic function in part B, we should actually get a different rate of change depending on which 2 points we choose. So with an x value of -1 and 3, our average rate of change should be 2. In part C, again, this is quadratic. So our average rate of change will depend on the 2 points that we choose. In this case, we should get an average rate of change of 0. Now, what that means is that if I look at this parabola, we've chosen 2 points with the same y value. And so the slope between those 2 points is actually just a horizontal line. And then lastly, in part D, we got to practice a little bit of computation and arithmetic with fractions. We should have, for this exponential function, an average rate of change of 20/3. Now, when you have answers like this, I don't want you to leave them in decimal form. It's more precise to leave them in fraction form, especially if the decimal is repeating or non-repeating. So if it's an ending decimal, you could put the exact value, but I prefer the fraction form. And on assessments, you will usually see that it asks for the fraction form. Okay. A little bit of vocabulary here. The initial value of a function, often referred to as the y-intercept, is f of 0. But really the initial value is just the b value, just the y coordinate. So when we're talking about lines, we often talk about y equals mx plus b, and we call b the y-intercept, but we know that a y-intercept should be an ordered pair, and b is just a number. So the proper term for that constant at the end of a function is the initial value. For our next example, we've actually already practiced our scatter plots on the calculator in our calculator lesson. So I'm going to actually have you do the scatter plot on your own, and we'll confirm it with you. But the new part of this section is correlation. And when we talk about correlation, we're talking about how closely the data represents the line that we calculate. So when we talk about the line of best fit or the linear regression, we're talking about the line that would go through these data points. And if all of the points are very close to the line, if I can encircle those points and it's a very narrow oval, then we say that this has a strong correlation. If that encircling is a little bit wider, and maybe I have a little bit more trouble envisioning where that line of best fit would go exactly, we say that that is a weak correlation. If I can't imagine whether the line would be a positive or negative slope, then we say that has no correlation. Same thing if I have a negative slope, but all of the points are very close to the line, we say that has a strong correlation. So how do we differentiate between these two strong correlations? We describe what type of slope it has. Here we have a strong positive correlation. Here we have a strong negative correlation. Here we have a weak positive correlation. And here, again, there's maybe a few different line of best fits that I can imagine. So this would be a weak negative correlation. So this whole diagram here on the side is for correlation. Now what I'd like you to do is practice those steps that we haven't done together in a few classes of finding the linear regression, the line of best fit for this data set. Let's go ahead and make this list 1 or our X values. We'll make this list 2 or our Y values. And then you're going to use that information, that equation, to predict what would happen if the prices were $2 and $4. Again, you'll put your answer into Edpuzzle, and then I will confirm your answer on the next screen. Okay, hopefully you got your linear regression as y equals negative 15,358.929x plus 73,622.5. And then if we let x equal 2, we can either substitute it here, or remember, you can use the table feature on your calculator. Can use second table for an x of 2 and an x of 4. Then we should get 42,905 boxes when x is $2 and 12,187 boxes when x is $4. Okay. If you want more reviews on specifically these steps, there is a folder in Schoology for calculator resources that will have reminders as well as the notes packet where we went over this before. On our last page, we have an example of transformations. We've already seen transformations. You had that art project to help kind of ingrain some of those transformations, help visualize what they're doing. And here we're just going to further apply it. Specifically, we're applying it to our x squared function, so our quadratic function. And then we're going to sketch this by hand without using our calculator. So the first thing I'm going to do is I'm going to look at g of x, and I'm going to look at what are the transformations that happened to x squared. And the key here is to perform transformations as the order of operations if you substitute x. So if I substituted a value for x, notice it would have been immediately squared. That tells me that none of my transformations are horizontal, right? Because all of the horizontal transformations happen before the parent function. They are grouped with x. So there are no horizontal transformations. My next transformation would be this flip and compression. So this is a reflection. A vertical reflection is over the x-axis. And compression vertically by 1/2. Compression, also called a shrink, vertical shrink by 1/2. Once I've done the reflection and the compression, the last thing is this +3. The +3 is a shift up 3. So if I start out with my parabola, I reflect it over the x-axis. It's going to go down like this. I compress it by 1/2. It's going to look wider. And then I shift it up by 3. I'm expecting my parabola to look like this. to plot exact points, you can make an XY table, starting with our vertex at 0, 3, and going out from there. 1 and -1 will have the same Y value. 2 and -2 will have the same Y value because of our axis of symmetry. But you can also use those transformations, right? In a normal parabola, from here we go over 1 up 1, over 2 up 4, right? Because 2 squared is 4 and 1 squared is 1. So if I use those same distances, but it's opening downwards and shifted by a half, then I go over 1 down 1/2, over 2 down 2, because I did 4 divided by 2. Over 3, normally it would be down 9. 9 divided by 2 is 4.5. Over 4, it would normally be 16. 4 squared is 16. So in half makes that 8. I think I counted too far. 4, 8, not this point. Right? So I'm using that transformation of 1/2 in order to calculate my parabola. If that doesn't make sense, just go ahead with the XY chart, not with your calculator. Do it by hand. So if I substitute 1 squared times -1/2 is -1/2, plus 3 is 2.5. Notice I went over 1 up 2.5. And then because of that symmetry, we know that these points are reflected over that y-axis. And so this is what our parabola should look like. Go ahead and try part B. Okay, start with just the transformations, and then I'll confirm that. Then I'll have you do the graph. So our transformations in order of operations, if I substitute into x, the first thing that happens is +2. It's grouped with x, so it shifts backwards. It shifts to the left by 2. Then I do the squared, so everything from here on out is a vertical transformation. Times 3 means a vertical stretch by 3. -1 is a shift down by 1. So if I kind of sketch through those transformations, this is what I'm expecting my graph to look like. Shifted left 2 and down 1 is going to give me a final vertex here in quadrant 3. Over 1, normally up 1, but times 3 makes it go up by 3. Over 2, 2 squared is 4, so normally we would go up 4, but now we're going up 4 times 3. So it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, just off the graph. Using that axis of symmetry, I'm going to go ahead and reflect these points to sketch my parabola without using a calculator. It is important to be able to do this without the calculator. However, you don't have to do it without any calculations. You could do an XY table. This time, instead of starting at 0, because the vertex shifted over, you would want to start at 2. Then +1 -1. So 2, 1, and 3. And those are going to actually have the same y value, so I can do it this way. And then +1 -1 would be 0 and 4. Now we can see from our graph that 0 and 4 are going to be much too large to graph on our plane that was given. So we have 2, -1. And then if I substitute in 1, 1 plus 2 is 3, squared is 9, times 3 is 27. I'm sorry, this should be negative. -2. Okay, this is going to make much more sense. -1 plus 2 is 1, squared is 1, times 3 is 3, -1 is 2. And that is what we get here. Okay, what I was calculating is when x is 1, it's going to be way high off of our graph. That's what I was trying to calculate before. Okay. So that is graphing through our transformations. The next part we actually went through in our mini lesson. So from here was our mini lesson last class. You can go ahead and copy that down or just put a note and refer to the notes that you took last class. This example 7 is the one that we did together last class during the mini lesson. If you've not turned in your worksheet that was for homework, if you can please turn that in, and I will have those graded and in the grade book and get those back to you. If you have any questions, feel free to email me or just come ask me when I'm back on campus tomorrow. Other than that, your homework will be on Math Excel, and that will give you a little bit more practice with these concepts.